So today we have yet another video looking at the cation exchange capacity, and we want to move towards looking at cation exchange capacity as it relates to changes in soil pH and therefore changes in soil acidity and alkalinity. So we know that the clay, mineral, and organic matter components of soil tend to have negatively charged sites on their surfaces, which adsorb and weakly hold positively charged cations. Now, the electrical charge is critical to the supply of nutrients because it's one of the ways that nutrients are retained in soils. So we could say that in general terms, soils with a large cation exchange capacity tend to be more fertile because they retain more cations. But productive crops and pastures can also be grown on low CEC soils as long as they're managed correctly. Anyways, so the main ions that are associated with the CEC in soils are exchangeable cations like calcium, magnesium, sodium, and potassium. And these are referred to as base cations. However, they're actually not bases, so maybe looking at them as non-acid forming cations or neutral cations might be a better way to look at them. So really they are not bases, but we do refer to them as base cations. So if the pH of the soil is not high, so if we have an alkaline soil, then if we just sum up all the base cations hanging onto these CEC sites, then we would have an adequate measure of cation exchange capacity. So let's do that for an example with a high pH soil. So we have a soil test result that came back to us, and in there we have 379 parts per million of potassium, 133 of magnesium, and so forth. Now we can look into our periodic charted table and look how many grams there are per mole of each one of these. So we have 39 grams per mole of potassium. Now in order to convert this to a cation exchange capacity, we need to actually look at, well, what is the atomic weight per charge? So for magnesium and calcium, because they have two charges, that number for the atomic weight actually halves, so that we now have, instead of 24 grams per mole of magnesium, we have 12 grams per mole of charge for magnesium. Now, parts per million really just means that there are 1 milligram per kilogram of soil. So for potassium, that'd be 379 milligrams of potassium per kilogram of soil. And taking all this together, we can now calculate what the contribution of each one of these cations is. So 379 milligram per kilogram divided by, now there's 39 grams per mole charge. We need to do some unit conversion so that everything is unit consistent, and we get to 0.97 centimoles of charge per kilogram of soil, which is the current unit for cation exchange capacity. But luckily, the current unit is equivalent in number to the previous unit, which was milliequivalents per 100 grams of soil. So potassium itself contributes about 1 centimole charge per kilogram of soil, and we do these calculations also for the other cations in it, and we'll see that calcium is a major contributor in this particular soil, meaning that the CEC, the cation exchange sites in this particular soil, are predominantly occupied by calcium, which is a good thing because calcium is one of the nutrients that is taken up in high quantities. So now we can add up the individual charges per kilogram of soil for these four cations, and we get to about 10 centimoles of charge per kilogram of soil, which for this soil equals the cation exchange capacity. And we would call this the CEC by basis method of determining cation exchange capacity of soil. So that works, of course, as long as there is no acid forming cations or acid cations occupying the exchange sites. So we have no protons or aluminum hanging on these CEC sites. And under these conditions, of course, you would also know that this soil has a 100% base saturation, meaning that 100% of the exchange sites on the exchange complex are being occupied by base cations. So what happens to the cation exchange capacity as we change the composition of the soil solution? So we know that we have these adsorbed cations, and we know that we have cations in solution, and that there's usually way more adsorbed cations than there are in solution by a wide margin. So if we add protons or aluminum, which we consider to be acid cations, we change the pH of the solution, if you so want. Now, why protons are considered acid cations is obvious, but aluminum, it's not so obvious. And there's a variety of reasons that we're going to have to talk about at some later time, but on this slide at least, it is because aluminum undergoes hydrolysis, and that frees up protons in the process. Okay, so soil acidification that normally starts by adding these acid cations and exchanging them for base cations on the exchange sites. So what happens is we have this active acidity, that is the one that you would measure with a pH probe in the soil solution, and we have this exchangeable acidity, and as we learned from the lytrophic series, protons have a much higher affinity to sit on these exchange sites than anything else. So if we have two protons, they get readily exchanged for the calcium that now goes in solution, and then from the solution it might precipitate out or be leached out or be taken up. Anyways, so what we've learned here is that, there actually is a mechanism by which if we add acid cations to solution, they get taken out of solution and adsorbed on these CEC sites. So the active acidity in the end did not change at all, but the exchangeable acidity increased because we added the protons there. So the pH change is resisted because we have cation exchange sites. And we call this the buffering capacity. And it's sort of important to remember that it is really just a buffering. The acid cations are not being neutralized. They are just being buffered, and eventually the cation exchange or the exchangeable acidity will be exhausted, and then the active acidity will increase as well. But it is a nice mechanism that helps you mitigate drastic and rapid changes in pH. So it helps to slow the process and provide a low-pass filtering to changes in pH. So as we just learned, the buffering essentially fills up the cation exchange sites with aluminum or hydrogen over time, if that is the progression of a soil. So now let's take a quick look at the graph that shows pH on the x-axis and the basically charges per kilogram soils on the y-axis. And we have exchangeable base cations, which are dominating the exchange sites at higher pHs, and exchangeable acid cations that dominate at lower pHs. So the curved line in between essentially is the inverse of the base saturation line. I've written it here as 100 minus base saturation, but you could also look at this as an acid saturation line. So now the exchange sites, of course, are not, or the number of exchange sites aren't constant, but they change with pH, as we've learned, and that is because part of it is a permanent charge, which will be associated with the clay minerals in which isomorphic substitution plays a big role, and pH variable charges, which happen on clays on the edges and particularly happen with organic matter and oxides. So on this green line then we have the cation exchange capacity by basis, or the potential cation exchange capacity here indicated as sort of the highest CEC at pH 8 and higher. And that's what we've calculated on the first slide of this video. But as you see, the CEC declines and we actually have an effective cation exchange capacity, or cation exchange capacity that is pH variable. And if you look into the soil web reports, you find the CEC reported at a pH of 8, at a pH of 7, and you find an effective CEC reported as well. So now that we know that CEC depends on pH, how CEC helps in turn buffer changes in pH, to resist changes in pH, let's talk about how changes in pH may come about. So every time we add protons to the soil, we tend to acidify it. Every time we add hydroxyls, we tend to alkalinify. And both of these will happen in soils, and it's the balance between these two that determines the long-term trend for a soil to change pH, which in most cases is going to be a change towards acidification of soils. Now, plants do play a role in this process, in the sense in that, as we've learned in the past, plants take up these base cations, but in order to maintain charge balance, they have to release an equal number of charges. So for every calcium 2 plus a plant may take up, it has to release 2 protons, thereby adding protons to the soil and aiding in the process of acidification. The plant also takes up anions, of course, but it does take up anions to a much smaller degree than cations, so that overall the biomass of the plant tends to be heavily biased towards being made up of base cations, especially calcium. Now, if we go in and we export that biomass, so we harvest it and we ship it off to market, we're also exporting these base cations. And that will lead to acidification of soil. And if we want to mitigate acidification of soil due to the export of biomass, we would have to reapply these base cations in the form of a fertilizer. So to give you a reference, 6 tons of alfalfa is a common number that can be harvested per acre. That contains 300 pounds of cations that the farmer would have to put back as a fertilizer. And on the Palouse, it's starting to be somewhat popular to export straw as well, and straw would have about half that number, so about 150 pounds per acre that are being exported in base cations in this process. So the other way that base cations may be lost from the process and lead to acidification is simply by leaching. So the more protons we add to the soil, because they preferentially attach themselves to these cation exchange sites, will result in base cations ending up in solution. They may combine with anions, leach out of the system, and leave behind a soil that tends to acidify. So let's go back to the plant. We have all the base cations accumulated in the biomass. They, of course, if they're not being exported, return to the soil in one way or the other. And not only the base cations, but also the organic nitrogen that was assimilated in the plant. Now, if the organic nitrogen is added back to the soil, undergoes ammonification and nitrification to turn it back into nitrate, which then can go back into the plant. Now, this goes in a cycle if the biomass is not exported. And you see that in this process, which involves ammonification and nitrification, we do release protons, which, as we said, would tend to acidify the soil. If this process actually does run as a cycle, these protons are being taken care of, and as long as it's a closed loop, it does not acidify the soil. And we will learn more about this as we talk about the nitrogen cycle in the coming weeks. But if we add additional nitrogen in the form of fertilizer, then this process will very obviously lead to the acidification of soils. So other processes that add to acidification, we've talked in the past how water and CO2 combine to form bicarbonate, and then how that might deprotonate and add protons to the soil. And we've learned that, well, because of respiration in the soil, we have a enriched soil atmosphere in terms of CO2, so this would be even more prevalent in the soil system than anywhere else. In addition to that, we as humans have caused acid rain, where pollutants in the atmosphere combine with oxygen and ozone to form sulfuric and nitric acids, which come back and interfere with aquatic systems, with forest systems, and also tend to acidify the soil. And then erosion as another natural and man-enhanced process also will tend to acidify the soil, and that is because with erosion we are moving cation exchange capacity off-site. So think about organic matter being moved off-site by erosion, and then with this CEC we also lose the base cations that are attached to these CEC sites. And then microbial decomposition, which is involved in ammonification and nitrification, but also in the breakdown of any other carbon structure, tends to deprotonate or add protons to the soil and acidify soils. Now that we know about where the protons are coming from that are causing changes in pH, let's talk about feedback mechanisms. One of the ones that we've talked about previously is the buffering capacity related to the cation exchange capacity in these exchange sites filling up with protons and aluminum as a way of resisting changes in pH. But of course there's more feedback mechanisms that are active there. One of them is that the cation exchange capacity declines as the pH decreases. We've looked at this previously. This is related to the variable charge on colloids, and as the pH then goes down, cation exchange capacity decreases, which also means that we increase the potential for leaching. More of these CEC sites are now being taken up by protons. Aluminum, calcium, magnesium, and other base cations are now in solution where they are susceptible to leaching. And for example, if we lose the calcium, we no longer have the following reaction present, which would actually take care of some of the protons in the soil. So we don't have those anymore. This neutralization reaction disappears, and we have a positive feedback loop where as we go towards decreasing pH, we tend to further decrease pH. So on this reaction, you also see why calcium is considered a base cation, because it does have this neutralization, quote unquote, reaction. The other one is as we increase the acidity of soils, or the concentration of protons, we also increase the weathering of minerals, which sometimes can be a good thing, because as we weather minerals, we also free up base cations, which can mitigate acidification of soils. But in minerals that contain a lot of aluminum, that becomes a positive feedback mechanism, because aluminum undergoes hydrolysis, and it does so as a function of pH, but either way it also releases protons. So you have more protons, you free up aluminum to hydrolyze, which then frees up more protons and tends to acidify your soil even more. And in addition to that, well, aluminum is also more soluble at low pHs. So what are all these effects on plant growth if you put them all together? So on this graph, we have pH on the x-axis, and you can see the concentration of protons and hydroxide opposite to each other. At pH 7, we said the concentration is equal, and the green line describes the effect on plant growth. So if we are at pH 7, then we have an approximate balance of the availability of micronutrients and macronutrients. So it turns out that at higher pHs, macronutrients such as calcium, magnesium are readily available, versus at lower pHs, micronutrients are readily available. And on the flip side, when one is available, the other one is not, and because a plant needs to have both of them, the pH range between 6 and 7 is optimal in terms of having availability of both macro and micronutrients. And if you go towards higher pHs, you run into micronutrient deficiencies. If you go to lower pHs, you run into macronutrient deficiencies. Now, if you go to the extremes, if you go to really alkaline conditions, now the solubility of metals, and most micronutrients tend to be metals, is so low that plants are really stunted by the lack of availability of these micronutrients. And if you go to the other end, if you go to acidic soils, then you see the before mentioned aluminum toxicity. Aluminum is more prevalent, becomes more soluble, interferes with a lot of plant functions. Aluminum toxicity takes over, and you also see calcium deficiency as one of the main macronutrient deficiencies at really low pHs, and calcium deficiency is prevalent there because plants do need a lot of calcium. So lastly, or second to lastly, I want to take another look at our 12 soil orders and the spodosols. So we've looked at these previously as one of the most beautiful, colorful soils to look at, where we have a leach layer, that is the white layer, and underneath it we get the accumulation of aluminum, iron, and organic matter that makes this nice dark color down below. Well, this kind of soil forms under acidic conditions. And the way the acidity comes about for spodosols is in a process called podsolification. And it usually happens when the parent material is relatively coarse-grained. So a granite parent material, for example, would weather 2 quartz, feldspars and some others that we said, but would end up being sort of a sandy soil that has really low cation exchange capacity, really little base cations available. So as the rock continues to weather, there's very little freeing of base cations, and it would also have relatively low water retention because, well, we have relatively large particles. You couple this with a climate in where precipitation outpaces evapotranspiration drastically. So it's a really wet climate where we have a really high potential for leaching. And the low water retention, the low water holding capacity, of course, also furthers that leaching where the soil doesn't hold on to water. It just moves to the soil profile. And with it, of course, it moves the aluminum, iron, and organic material. And it also is a relatively cool climate soil. And of course, the coldness of the soil influences the biota and causes little microbial decomposition because temperatures are low. But the other factor that causes that is the vegetation that grows on it. Most of the spodosols, not all, we find under coniferous forests. If you think about needles falling on the ground, they're not very easily decomposable. They accumulate there. So whatever base cations were accumulated in the biomass are slowed in the process of being returned back to the soil, and then we also have relatively little mixing. So all these factors taken together lead to a soil that has acidified, it has declined, there's more protons being released than there are being neutralized or buffered or taken care of in any other way, and we create these kind of spodosols. So really lastly here, a quick look at a map of the pH in the continental US. You'll see the warmer colors, those being more acidic soils, the cooler colors, those being more alkaline soils. And if you look at this closely, you see a close association with the parent material, so the geology of the US, the climate, so precipitation and temperature, as well as the vegetation. And what we've learned hopefully in this video is that we as humans also add to these pH changes to management choices that we make either in forest systems, range systems, or ag systems, where it's especially fertilizer additions that tend to acidify the soil, as well as harvesting of biomass and exporting it, as well as the way that we manage organic matter in soils. So for the mitigation piece of, well, if you do see changes in pH, whether you acidify the soil or you alkalinify the soil, there's of course ways that you can mitigate for that, but all of them are going to involve some effort and some cost, and I will let you read that in your textbook.